continue on with Chapter 29 on electromagnetic induction. And we really, this is going to sound kind of funny, but I've said this many times before, really are kind of done. What we have discovered is that when you have movement of charge through a magnetic field, you create a potential difference, or you can create a potential difference. And we figured out that that potential difference, although we using the Lenz force, we figured out that there's a shortcut way for doing this, and that shortcut way is to look at the change in the magnetic flux with respect to time. And then the negative of that will give us the potential introduced. Okay. There is, however, one more kind of, well, there are two things. First of all, there's a philosophical thing. That change in the magnetic flux, when we did that earlier example, the change in magnetic flux came from the motion of charge, moving charge. But it turns out that that is not necessarily the only condition under which magnetic flux will change. If I have a region that has a magnetic field, and at time t equals 0, if I graph the magnetic field, I'll do this, the magnetic field strength in the z direction, if I graph that, if it starts out here, and then it goes down negative, and then it gets bigger, if I have a changing magnetic field through some area, so here's some area, my flux is equal to just BA in this particular case, because I'm assuming B is normal to this. So my flux is equal to B times A, and B is changing. So is there any motion at all? Is there any QV? No, there is not. However, in the same way as when in class we talked about that sheet of uniform charge, and someone who is just racing by the sheet of uniform charge that is not moving as far as we're concerned, do they sense a magnetic field from it? Well, yes, they do. In the same sense, there is a electric potential introduced even when you don't have a QV that we observe. It's actually the same source, and it really is more or less the same thing as that person running by the uniform sheet of charge. But philosophically, it's very interesting to note that the change in magnetic flux is really what's responsible for the generation of an electric potential, regardless of the source of that change of flux. It can be motion. It doesn't have to be motion. Okay. However, there is one thing that one rule we can use. Let's say we have a loop of wire here, and this loop of wire is put into a magnetic field with some certain strength. Let's say the strength of this magnetic field changes. So here I am with some B0. Let's say it just goes like that. So this magnetic field is pointing, as far as you guys are concerned, let's see if I can, once again, I don't know if this looks right when you guys do it, so I think I do have to do this backwards to make it look like a right-handed system to you. X, Y, and then Z would go towards you. So this would be B0 in the Z hat direction. Okay, however, the B0 Z hat is changing. So here's my loop. My loop has some area. Well, let's just go ahead and call it pi r squared because it's a circle. And so what's the flux? It's B0 pi r squared. So what's the change in flux with respect to time? It is just pi r squared dB0 dt. And then this just happens to be a line, so it would just be some number here, right? So just whatever the slope of this line is, which happens to be a negative slope. Okay. So for this particular situation, this would just, I'm just going to go ahead and say, yeah, just think of m as negative, but we'll just say it's m pi r squared, where this is just, m is just the slope. Okay. However, what do we want to know? We want to know the direction that we want to know the direction that the current will move to try to create a potential difference in response to a changing magnetic flux. And there's a very simple way to do that. It's called Lenz's law. For Lenz's law, this is what we do. We say, look at the change in the magnetic flux. The system wants to oppose the change in magnetic flux. So, for example, right now we have a magnetic field that's in this direction, but it's getting smaller in that direction. This system does not want that magnetic flux to get smaller. It wants it to stay where it was to begin with. So it is going to create a current that will offset the change in magnetic flux. So if the flux is decreasing in this direction, it's going to create a current that will increase the flux in that direction. So what is that? Well, that's, once again, this is just a loop. This is the simplest right-hand rule. Put your thumb in the direction of the magnetic field, and your fingers will curl in the direction of the current. So we will have a current that is induced in this direction if our magnetic field is decreasing in that direction. If it was increasing in this direction, if the magnetic field is increasing in that direction, this current now will try to oppose that. So it says, oh, I don't want this magnetic flux to get bigger. I would like it to stay the same. So it's going to fight against the change. So it's going to try to produce a magnetic field pointing in this direction. Well, what does that mean? That means the current would then be going in this direction, opposite. There's only one more thing that I want you guys to get out of chapter 29. Only one more thing that you need to kind of understand. This is what happens for one loop. The flux here produces a voltage, a potential difference of this much for one loop. But what does it do? What if there was another loop right underneath this? It would produce that same potential difference. And another loop right underneath that. If those loops were all joined together, the potential differences will add. So if you have a coil of wire, that has n loops in it, then our potential difference will be n times the change in the magnetic flux per time. And that will be our V that is produced in this coil. And that's it. That's what I want you to get out of chapter 29.